Hey everyone, and welcome. Today, we are diving deep into energy. You know, that invisible force that's behind basically everything that happens, from the tiniest atom to the biggest star. It's the power of movement and the power of just being in the right place. All right, let's jump right in. So, to get our heads in the game, I've got a little puzzle for you. What is the hidden connection between a coconut falling from a tree, a car speeding down the highway, and a rubber band that's been stretched to its absolute limit? Believe it or not, they all share a fundamental secret, and by the end of this, you are going to know exactly what it is. All right, to crack this puzzle, our first clue is actually hiding in plain sight. Let's take a look at the secret power that's lurking inside totally ordinary everyday objects. I mean, think about it. A cricket ball moving so fast it can just shatter a wicket, or a hammer held up high, ready to drive a nail into a piece of wood. What about a wind-up toy car, all coiled up and ready to go? Or a bowstring pulled all the way back about to launch an arrow? In every single one of these cases, whether it's through motion or position, the object has gained the power to make something happen. And in physics, we have a name for that. We call it the capacity to do work.
So, what is this shared capability? This hidden power? It all comes down to a single, incredibly powerful concept that scientists call energy.
The official scientific definition is actually beautiful in its simplicity. Energy is just the capacity to do work. That's it. So if an object has energy, it can push or pull on another object. And when it does that, it can transfer its energy, causing a change, like making that other object start to move. And get this, energy and work are so tightly connected, they even use the same exact unit of measurement, the joule, which we show with a capital J. This basically means that whenever you measure work being done, what you're really measuring is the exact amount of energy that got transferred in the process. They're two sides of the same coin.
Now, energy isn't just one single thing, right? It comes in all these different flavors. You've got heat, chemical energy, electrical, light. But for our puzzle today, we're going to zero in on mechanical energy, which is really just made up of two key types that we've actually already seen in our examples.
Let's start with the first one, which is all about movement. This is the energy you see in that speeding cricket ball and the fast car we talked about. This is what we call kinetic energy.
So, kinetic energy is simply the energy an object has because it's moving. And the faster it moves, the more kinetic energy it's got. It makes sense, right? A car going 100 kilometers an hour can do a lot more work, and yeah, that means damage, in a collision than the same car just crawling along at 10.
We can even calculate it with this really neat formula. Kinetic energy, or EK, is 1/2 times the object's mass, m, multiplied by its velocity, v, squared. Now pay close attention to that velocity part. It's squared. That means if you double an object's speed, you actually get 4 times the kinetic energy. That's a huge deal.
Okay, to see this thing in action, let's plug in some actual numbers. Imagine an object with a mass of 15 kilograms, about the weight of a bicycle maybe, and it's moving at 4 meters per second. You run the math, and boom, you find it has exactly 120 joules of kinetic energy. That is a real, measurable amount of power, all generated just from its motion.
Okay, but what about the raised hammer or the stretched rubber band? They aren't moving, but we know they've got some kind of power packed away in them. Well, that stored power is our second type of mechanical energy, potential energy.
Potential energy is, you guessed it, stored energy. It's the energy an object holds because of where it is, like the hammer held high above the nail, or because of its shape, like that stretched out rubber band. It's energy that's just waiting to be released. It's pure potential. For things being lifted up against gravity, we calculate their potential energy with this formula. EP equals the object's mass, m, times the acceleration due to gravity, g, times its height, h. It's pretty simple. The higher you lift something, the more stored energy it's got.
So let's test this one out. If we take a 10-kilogram object, I'm picturing a heavy bowling ball, and we lift it 6 meters off the ground, we've just done work against gravity. And that work doesn't just disappear. It gets stored as 588 joules of potential energy, just waiting for us to let go so it can transform into something else.
Okay, so let's put these two side by side to make it super clear. Kinetic energy is the energy of motion. It all depends on velocity. Potential energy is the energy of position or shape. It depends on height. A running athlete is just packed with kinetic energy. A stretched rubber band? That's pure potential energy. See, they're two sides of the same mechanical energy coin.
So we have energy of motion and stored energy. But how do they connect? Well, the final piece of our puzzle is one of the most fundamental laws of the entire universe, and it explains that energy never really goes away.
This brings us to the law of conservation of energy. It's a non-negotiable rule of the cosmos. It says you can't create or destroy energy. You can only convert it from one form into another. The total amount you start with always stays the same, no matter what.
Let's watch this happen with a falling object. It's the perfect example. At the very top, before it's released, all its energy is potential. It's maxed out. Its kinetic energy is zero. Then, as it falls, you see the trade-off. That potential energy starts to decrease, and in its place, the kinetic energy starts to increase. And then right before it hits the ground, almost all of that stored potential energy has become the energy of pure motion. But the total energy, the potential plus the kinetic, that number stays constant the whole way down.
And just like that, we've solved it. The hidden connection is energy itself. The falling coconut is converting its potential energy into kinetic energy. The speeding car is full of kinetic energy, and the stretched rubber band is just loaded with potential energy. They all possess the capacity to do work.
But let's ask one final, important question just to make sure this really sinks in. If the potential energy of a falling object is going down, doesn't that mean we're losing energy? Does that violate the law?
Absolutely not. The energy isn't just vanishing, it's transforming. For every single joule of potential energy that disappears, an equal amount of kinetic energy appears. The universe's energy books are always perfectly, constantly balanced.
So I'll leave you with this final thought to chew on. Imagine a world where energy was just stuck in one form, where potential energy could never become motion. What would that be like? Well, nothing would move, nothing would change. Life itself, which is really just a series of incredibly complex energy transformations, just wouldn't be possible. Pretty wild to think about, right? Thanks for watching.